everyone. Hello and welcome to the Structures Lab 3 video presentation. My name is Henry.
My name is Shiv.
My name is Sajad.
And today we'll be going over an overview of the Shear Center Design Lab. So first up, I'm going to give just a brief review of Shear Center. So we're going to be talking about when shear loads pass through the shear center. This will result in a no twist, so you will have only pure bending. And if the beam cross section has an axis of symmetry, the shear center will lie on that axis. Now, say you have a load applied off axis, well then you will produce a torque on that beam. And in this case, you would have to account for both the torsional and the shear effects on that cross section. This is a pretty good visual presentation of my explanation, showing the steps in applying a torque to your system. Now, next, we need to first find shear flow before getting to shear center. And shear flow is basically shear stress per unit length. And through this representation, we have a pretty lengthy formula. This is the Euler-Bernoulli beam bending formula, beam bending theory. And the way this will be used is that it takes into account the force applied, the second moments of area, and the thickness that is calculated per each section separately, and then total for a final shear flow across the cross section of the beam. Now, when we have this, we can finally move on to getting our shear center. Now, an assumption for the shear center is that we have 0 moments about the shear center, so then we can basically formulate a solution in the form of this, which basically explains how to get the shear center location and takes into account shear loads and the torsional effects on the cross section. So as a final note, this is basically 2 different methods on calculating both open and closed sections. Usually closed sections require a little bit more calculation, because now you have to take into account solving for the shear flow at the origin, which is typically 0 for open sections. So there's a little bit more work required with closed sections, but generally for closed sections you can apply shear loads at points off the shear center and still have the shear stresses caused by the torsional and shear loads be constant across the thickness. But that is generally not the same case for open section beams.
Over here we have the experimental apparatus. On my right you have the top view, and then there's a side view. On this view we're using 2 potentiometers, basically 3 inches apart from the center. We are using like a white plate, and that's to represent where the string is on the notches. The notch is attached right over here, and the column goes basically under it. The column is mounted using an Allen fastener, and we added the weight or inputted the weight over here. The weight you can add more weight. For our experiment on the C and the L beam, we used 5 pounds. We used the pulley system to hold the weight, and the wheel could move basically on this axis as your notches. In this slide we have the top view to explain more how this experiment we conducted. The notches, there are 13 notches. Each notch is 0.21 inches apart, and we set our notch distance for our 7th notch to be 0. That will be discussed later in the results. And over here, the notches have to line up with the black lines in order to differentiate each line and move 0.21 inches apart.
So before we began the experiment and collecting data, we took the dimensions of the 2 beams that we used. The first beam that we tested was the C beam. These are the dimensions of it. We also assigned a coordinate system to the cross section with the X going in the horizontal and the Y going in the vertical. We did the same coordinate system for the L-beam, where the L-beam is oriented in a V. The L-beam dimensions are labeled right here. So for the procedure of this lab, we first started at the first notch to the left. So we lined up the pulley wheel with the notch so that the string would go along the black line as discussed previously. After we aligned it with the notch and moved the pulley wheel, we took potentiometer readings from the left and the right and recorded it for that position. We then began moving this notch down by each single notch and also moving the pulley wheel so that the string would line up with the lines, and then we would take readings at each single notch. Down here in this picture you can see that this was during the 8th notch, one to the right of the center, and then we recorded the data there. We repeated this procedure for the L-beam as well.
Okay, so now we'll talk about the results of the C-beam. Over here we plotted the voltage as a function of the notch distance. 0 represents the center notch, basically where the left and the right potentiometer data readings will be intersecting or approximated at. Now over here, the blue line and the blue dots represent the voltage versus distance of the right side of the beam from readings from the potentiometer. We use LabVIEW to get the readings, and the linear fit line, the blue line, represents the linear fit line from the Excel. The orange dots represent the notch distance or voltage versus notch distance from the left side, and the linear fit line was also conducted on that axis.
So using these two equations that we got from Excel, we solved it as a system to find where the two lines would intersect. Where these two lines intersect would give us our experimental shear center. So for the C-beam, we got our experimental shear center to be 0.0138 inches to the right of the center. This was a little off from our theoretical prediction in the beginning. We predicted that the shear center would be at 0, given that the beam was symmetric and the shear center must lie on the symmetric axis, as theory would tell us. And looking at our value, we have 1.38% error.
Okay, so using similar procedures, we ended up getting the results for the L-beam specimen. We plotted voltage as a function of the notch distance, and the experimental data we had plotted the trend lines, and then we calculated the shear center to be at an intersection point of about negative 0.0164 inches.
So given that we got negative 0.0164, that was a little off from our theoretical shear center, which was at the neutral point axis. Given that we loaded the L-beam in an angle so that it would be a V, we did this so that the shear axis, the symmetric axis would go along the y-axis when x equals 0. So we had a 1.64% error when calculating the shear center for the L-beam.
Okay, so just some quick takeaways. Upon completing this lab, we ended up concluding that we have accurate experimental apparatus, and we have an easily repeatable experiment, so we can get similar results in the future.